In the last video, we made this table of binomial coefficients for small values of n and k. I actually, in between, I added another row just for fun for 7. So what I want to do in this video is to try to look for some patterns that we see in this table and see if we can make sense of why those patterns appear. So the first pattern that we see, it's very obvious that there's some symmetry here, right? So this table, like each row is symmetric from left to right. So if you flipped it right to left, you would get the same thing. And we kind of already knew that because in a previous video we argued that n choose k is always equal to n choose n minus k. And that's exactly what we're seeing show up here. So, here is like, for example, this 15 is 6 choose 2, and the other 15 over here is 6 choose 4, which is 4 is 6 minus 2. So that's where we're seeing that symmetry come up. Another pattern, there's lots of patterns that we could notice. Another one I want to talk about is what happens when we add up the numbers in each row. So if I add up, well, this row is just, that blue is probably hard to see. Blue is green. So we get 1 here. If we add these up, we get 2. If we add these up, we get 4. 3 plus 3 is 6, plus 2 more 1s is 8. Okay, 1, 2, 4, 8. That's looking a little suspicious, right? Let's try this one. So 4 plus 6 is 10, and then I've got another 4 and 2 1s, so that's 6, so 16. And we can verify, this is very easy. 10 plus 10 is 20, plus 2 more 5s is 30, plus 2 is 32, and so on. So there seems to be clearly a pattern here. We could conjecture that the sum of, these are obviously powers of 2, right? So we conjecture that the sum of row n is always going to be 2 to the n. Okay, so sum of row n equals 2 to the n, right? And we could write this even more formally and say, right, we're conjecturing that the sum as k goes from, well, let's just say when k is between 0 and n of n choose k is equal to 2 to the n. Question mark. And how could we prove this? So one way we could prove it is we could, use this formula and write this out, maybe use some kind of induction and add these up, and it would be really tedious and a lot of details, and I don't want to do it that way. Okay. I really only want to use this formula for computing values of binomial coefficients. I don't want to use it as the definition. Okay. This is not the definition of n choose k. The definition is it's the number of ways to choose k things out of n. That's the definition. And we just derived this formula that lets us compute that. So can we prove this just by arguing about counting things? That's the ideal. And we can. So here's how we argue that this is true, just by thinking about what it means in terms of counting things. So each binomial coefficient, n choose k, is the number of ways to choose k things out of n. That's the same as saying the number of subsets of size k of a set of size n. And so, for example, if we look at the row for 4, so this is, this is the number of size 0 subsets of a set of size 4. This is the number of size 1 subsets. This is the number of size 2 subsets, and so on. And if we think about this, right, every subset, if we take a set of size 4 and we look at every possible subset gets counted exactly once in here, right? Because each subset has a size, and it's going to show up in the count for subsets of that size. These don't overlap at all because we can't have a subset that has 2 different sizes at once. And these cover all the possibilities, right? Every subset is going to have some particular size, and a subset of a size 4 set has to have a size between 0 and 4. And so by the sum rule, right, adding up all the numbers in a row should give us the total number of subsets of a set of that size. And we already know that the number of subsets of a set of size n is in fact 2 to the n. Okay, so that is a proof that this is always going to be true. Another pattern that we notice, and this is probably familiar to you if you've looked at Pascal's triangle before, right, is that each entry in the table is equal to the sum of the two above it. So like one right above it and one kind of above it and to the left. So for example, okay, this 10, right, is equal to, that 4 plus that 6, right? So 15 is 5 plus 10. 6 is 1 plus 5. It even works for the ones on the sides if we remember that like things off the table are supposed to be 0. So this 1 is like 0, the 0 over here plus 1, right? This 1 is like 1 plus, there's a 0 here. The only thing it doesn't work for would be this 1, because I guess there'd be zeros up there. Although, it turns out it can actually make sense to define it for negative things, where you get kind of a flipped copy of this with some negatives up there. But I'll let you think about that if you want. So what we're conjecturing is, let's think about how to write this generically. So for this particular example, like here, 5, we're saying 5 choose 2 is equal to 4 choose 1 plus 4 choose 2, right? So it's always, whatever n is, we're adding up two things with n minus 1, and one of them has the same value of k, and one of them has a value of k 1 less. So we're saying n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. Right, so this is the thing directly above it with the same value of k, and this is the thing above it and to the left with a value of k 1 less. So again, we could prove this by writing down, this formula for these and doing a bunch of messy algebra with, you have factorials, canceling, and factoring things out and stuff like that. But that's not how I want to prove it. Again, I want to prove it just by talking about counting things. So here's how we can do it. Again, this is the number of ways to choose k things out of n. So I have my n things. I'm just going to arbitrarily label, look at one of the things and call that thing 1. Okay? So, and then we're going to use the sum rule and say, well, every way of choosing k things, either I choose thing 1 or I don't. And those cover all the possibilities, right? Either I'm going to choose thing 1 or not. And they also don't overlap, because any choice where I do choose thing 1 is different from a choice where I don't. Okay? So by the sum rule, the number of ways to choose k things out of n is the same as the way to choose k things out of n where we don't choose thing 1, and the number of ways to choose k out of n where we do choose thing 1. Okay, so that's what this, and I'll argue in a minute why these are the right values for that. So this is the number of ways to choose k out of n without thing 1. And this is the same, the number of blah, 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 with thing 1. Okay, and why are these the right expressions to count this? Well, so first of all, let's say that I don't choose thing 1. How many ways do I have to choose k out of n things where I do not choose that first thing? Well, since I didn't choose that first thing, I'm now left with only n minus 1 things to choose from, and I still have to choose k things, okay, because I haven't chosen anything yet. And so the number of ways to do that is the number of ways to choose k things out of the remaining n minus 1. Okay, and what about this? If I do choose thing 1, now I still have n minus 1 things left to choose from, but now I already have one thing in my set, and so I only need to choose k minus 1 to sort of fill out the rest of my choice of k things out of the remaining n minus 1. And so that, again, that is a valid proof that n choose k is always equal to the sum of these things. I will leave you with one more pattern. So there's tons and tons of patterns in Pascal's triangle in binomial coefficients. We have really only scratched the surface. So I will just point out One more pattern that I particularly like. I'm not going to prove it to you. I'll let you play with it and see maybe if you can prove it. I do know a way to prove it, so if you want to know, you can come ask me. I'll show you. But you can look for other patterns yourself, and there's tons of patterns you can find in here. So here's the pattern I want to point out. So we added up rows of this before. If I instead add by diagonals, so if I look at, so that diagonal is 1, this is 1. If I add up along this diagonal, I get 2. If I add up this diagonal, I get 3, 1 plus 2. Here, 1 plus 3 plus 1 is 5. 1 plus 4 plus 3 is 8. 1 plus 5 plus 6 plus 1, let's see, that's 6 plus 6 is 12 plus 1 is 13. Okay, and these numbers are probably familiar to you. Those are the Fibonacci numbers. And so the question is, does that pattern continue? Probably yes, right? And if so, why?